we are going to learn an interesting topic, that is how waves are classified. We will see which wave need a medium to travel and how the direction of the wave as well as the motion of the particles of this wave help us to classify them. So let us begin. So now the topic is all about classification of waves based on the necessity of medium. Children, based on the requirement of the medium, waves are generally classified into two types. One is mechanical wave and the other is electromagnetic wave. Remember children, mechanical waves are also called as your elastic wave. So let us try to understand them one after the other. So coming to the mechanical waves. What is meant by mechanical wave? The waves which require a material medium for their propagation is called as your mechanical wave. I repeat, the waves which require a material medium for their propagation or transmission are called as your mechanical wave. So that means these waves may require either of the solid, liquid or gas for their transmission. So these type of waves, mechanical waves, can never travel through vacuum. Now if you look at the examples of mechanical waves, so you can consider the vibrations in a rope. If you take a rope, produce some disturbance at one end of the rope and these disturbances are traveled along the rope to the other end. So the vibrations in a rope come under the example of mechanical wave. Not only this, vibration of a particles in the stretcher string or the vibration of particles on the surface of the water also come under mechanical waves. Okay children, sound waves in air are also considered as mechanical waves because all these waves require some medium for their propagation. The first example, the rope. Second example, stretched string. Third example regarding the water surface, the surface of the water, and the one more example I gave you regarding the sound waves in air. So all the air molecules and all get disturbed here because of the disturbance we have created in the form of energy, and this has been carried from one point to the another point. So all these examples require some medium for their propagation. Okay, so this is all about your mechanical waves. Now let us try to understand electromagnetic. What are electromagnetic waves? The same thing. So the waves which do not require any material medium for their propagation, okay, they are called as your electromagnetic waves. For example, light waves if you consider, okay, that means the electromagnetic waves can even travel through vacuum. I told you that mechanical waves can never travel through vacuum, whereas electromagnetic waves can travel through vacuum. So light waves, gamma rays, infrared rays, X-rays. So all these types of rays or radiations come under this category. So electromagnetic waves. The best example is a light wave. Okay, so these electromagnetic waves generally travel with the speed of light. That means the speed of electromagnetic waves is in around 3 into 10 power 8 meter per second. So electromagnetic waves travel with a speed of 3 into 10 power 8 meter per second. So as I told you, the examples for this are light waves, gamma rays, sound, infrared rays, X-rays, microwaves and so on. So now let us move to the other classification of waves. So children, now let us look at the another classification of waves. Children, on the basis of the relative direction of propagation of the wave, I repeat, on the basis of the relative direction of propagation of the wave with respect to the direction of the changes in the medium. What type of changes? The changes can be like displacement, pressure, density. So based on these factors, again waves are classified into two categories. One is longitudinal waves and the other is transverse waves. Let us try to understand them in detail now. So first of all, what are longitudinal waves? Okay, so a wave in which the particle of the medium vibrate to and fro or back and forth. That means, let us suppose that a wave travels from left to right as shown in the figure. So this white color Let us suppose that a wave travels from left to right as shown in the picture, that white color line segment. Okay, so and let us suppose that these yellow color dot marks, okay, here this one, this and all. Let us imagine that those are the particles of the medium. So the direction of the propagation is given as the white color line segment, as well as the dotted lines represent the particles. So whenever a wave is propagating, in this example, whenever the wave is propagating from left to right, all the particles of the medium also start vibrating parallel to the direction of the wave propagation. Okay, that means this orange color, if you look at it, the particle, that yellow color particle is moving to and fro, back and forth, or that means they are vibrating parallel to the direction of the propagation of the wave. So this type of waves generally come under this category. So what are they? Longitudinal waves. So that means in longitudinal wave, the particles of the medium oscillate or vibrate to and fro or back and fro. That means parallel to the direction of propagation of the wave. Okay, children. So in this case, the better examples for this longitudinal waves are sound waves and air come under this longitudinal waves. So, as well as waves produced in the spiral spring also are categorized as longitudinal waves. So let us try to understand these longitudinal waves in detail. So here if you observe that this case, the second case, this is the first case and here is the second case. Two graphs I have given you some representation of the wave. So here let us suppose that the particles of the medium distributed evenly as shown in the second picture. That indicates that, so the equal spacing is there between the first particle, second particle and third particle. Equal spacing means, so this indicates the density of the particles. So the second figure indicates the normal density of the particles. What is this, children? Normal density. So what do you mean by normal density? So this is your normal density. So in this normal density, you can observe that the equidistant, each and every particle is equidistant from each other. But if you compare to the first structure, here if you observe that from this particular region, okay, so from here to here, more number of particles are concentrated. That means density, more number of particles means more denser. Okay, so large density, denser particles. Whereas if you compare from here to here, this particular region, so less number of particles are being concentrated. So what does it mean, children? This part is called as a rarefaction. This is called, so when compared to the normal density of the medium, here more density is there, here less density. Again from this region you have larger density when compared to the normal density, and again here lesser density when compared to the normal density. Again here also larger density when compared to the normal density. So like this the waves have been distributed. The particles are spaced. So let me extend this picture, children, for your clarity. Okay. This may give you more clarity. Here also let me continue the picture. This is better. So this part is your compression. If you observe wherever the density of the particles are larger when compared to the normal density, they are generally named as your compressions, and the area where the density is lesser when compared to the normal density, they are generally termed as your, so this part is your rarefaction, whereas the other part where larger density is there, that is termed as your compression. So you can see that in the picture, alternate compressions and rarefactions are formed. So this is your compression, rarefaction, compression, rarefaction, compression, rarefaction. So on and so forth. So what is a compression, children? Whenever the density of the particles are larger when compared to the normal density, they are generally called as compressions, and wherever the density of the particles are lesser when compared to the normal density, they are called as a rarefraction. So whenever a wave propagates along a medium, okay, whenever a longitudinal wave propagates along a medium, we observe that an alternate compressions and rarefractions are formed. And always remember that, children, the distance between the compression, two successive compressions, that means from here to here, the distance between two successive compressions from here to here, or the distance between two successive rarefaction, that means from here to here, if you observe, the distance between any two successive compressions or any two rarefaction is always equal, and it is equals to a wavelength. So it is also called as a wavelength, indicated with the letter lambda. The distance between any two compressions or rarefactions are generally called as a wavelength, represented with the letter lambda. The phase difference between any two successive compressions or rarefaction is equals to 2 pi. The phase difference, okay, that means 1 lambda is equals to 2 pi radians. Okay, so the same distance, whatever you considered it as a wavelength, in distance mode if you consider it as wavelength, in phase wise you consider it as, we'll discuss regarding the phase and all in later concepts. The phase difference between any two compressions and rarefactions is always given by 2 pi radians. Children, one more thing you remember, that longitudinal waves can travel through solids, liquids as well as gases. So now let us also look at the graphical representation of this longitudinal wave. So what the complete picture resembles the longitudinal waves, children. Longitudinal waves. This is all about your longitudinal waves. So I would also like to explain you in detail regarding the graphical representation of this longitudinal waves. For this, let us consider the coordinate system in which x-axis and y-axis are being taken. Clear? So in this, let me mark it as some OX, OY and OY dash respect. So if you consider this some wave may transferring like this. So let us consider this OX, this horizontal line. OX represents the normal density of the wave. This represents the normal density of the wave. Let OX represents the normal density. So all the waves or all the particles above this normal density line are, let us, comparatively of larger density, and all the particles below the line OX are of smaller density. So these are of larger density, above line are of larger density, whereas below line represents some smaller density. I already told you, children, wherever we get across the larger density, they are called as your compressions. That means the above waves, this, everything represent the compression, and the below things represent your rarefaction. So let me always represent compressions with the letter C and rarefaction with the letter R. Okay, so this be R and here it is R. So larger density are generally termed as your compressions, and as smaller density called as your rarefaction. And let this OX line, the horizontal line, let it be some normal density. The same thing can be represented on a graph as shown. Okay, children. So now let us also try to understand the concept of longitudinal wave, how these longitudinal waves will be transmitted in the case of a spiral spring. The other name of spiral spring is also called as your slinky. Okay, slinky is nothing but that spiral spring. So if you imagine a spiral spring, something like this, normal spring. Well, so it's a long flexible spring that can be compressed and extended. So this is a spiral spring. We can compress it and we can even extend it. So that type of compression, wherever in a spring, whenever the compression and extensible is possible, the other name for it is also called as your slinky. So let us try to understand how the longitudinal waves are transmitted in the case of a slinky. So whenever you press the one end of a spring, then what happens means here the spring takes the new form as something like this. Okay, and wherever it is relaxed, in that case the spring will be something like this. Again compressed and again relaxed. Okay, so if the free end of the spring is moved to and fro continuously, this is the free end of the spring, children. If you start moving it continuously to and fro, then what happens means at some particular region, so more helical structure is observed, and some other cases the spring is like it's simply released. Okay, that means large amount of gap is there at some particular region and less gap, large gap and less gap alternately is formed. So like this is generally termed as your compression and this is called as your rarefaction. So in a spiral spring or a slinky, whenever it is force is applied at the free end and continuously it is pressed and released, pressed and released. So longitudinal waves are produced in the case of spring, in the case of slinky, and it is being transferred from one point to the another point along its length. Likewise, alternate compressions and rarefactions are observed in the case of your slinky.